Here we are, the last topic on periodic trends. Now, before we go too crazy, I should mention a couple things. Number one, this is not in the textbook. It's nowhere in the textbook, so if you're digging around, you're not going to find it. This was added with the last curriculum adoption to the AP test. So most textbooks don't have it in there unless your district is going to go ahead and buy brand new editions of all the textbooks. So this is where you're going to find most information on PES, Photoelectron Spectroscopy, or at least anything that you need to know. Or you can also find lots of websites that will kind of go into more detail. But I mean, this is really all you need to know on PES, and you're going to love it. The other thing that I think I forgot to mention in an earlier video, isoelectric ions. Make yourself a little note. Remember isoelectric ions? Those ions that have the same number of electrons? Technically, that is found in Chapter 8 of your textbook. But the AP test will kind of lump that together with the trends because we really think about isoelectrics as like a trend in ionic radius. So I pulled it out and made sure that we covered it now with periodic trends. But if you're looking for a further explanation of isoelectric ions, it's actually in Chapter 8, which is on bonding, and it makes no sense. But it's pages 340 to 342. And specifically, you might want to see some sample exercises. There's like an 8.3 and an 8.4. There's really not a lot of practice problems, homework problems in either Chapter 7 or 8 that deal with these isoelectric ions. But these two examples in the sample exercises are excellent. So for isoelectrics, if you want more information, check Chapter 8. This PES, Photoelectron Spectroscopy, you're not going to find in the textbook. But actually, this is some good stuff. This makes sense. Here's the point of it. It's a lab technique, which is why the AP test wants to kind of look toward this. They're looking for data that supports atomic structure. Why do we think that there are orbitals? And why do we think that certain electrons have greater ionization energy than others? They might be further from the nucleus, or there's more attraction, or whatever. This PES, Photoelectron Spectroscopy, is a laboratory method that kind of confirms the idea of orbitals, and there being lower energy orbitals and higher energy orbitals. And it kind of also confirms how that would affect ionization energy, the amount of energy needed to remove electrons. So now, in general, here's what this is. It's a procedure where you'll have some kind of an energy source that's shined on the surface of your element. This reminds me of some other atomic structure experiments too. So you'll look at the minimum frequency of light needed to remove electrons. So we're talking ionization energy here. So we're trying to remove electrons from the surface of a particular sample. And we look for that threshold energy, the least amount of energy required to get those electrons moving. If we add more, the electrons just come off with greater kinetic energy. They just have more energy. They're moving faster. Reminds me of the photoelectric effect, huh? Here's the kind of data that we get. It's these graphs. So PES data, photoelectron spectroscopy data for hydrogen and helium, looks kind of like this. You'll have energy, and specifically this is ionization energy. Oh boy, thinking ionization energy, and it's usually measured in units of megajoules per mole. So if you see that unit MJ, it probably refers to megajoules per mole. Okay, so we're looking at the ionization energy, the energy required to remove electrons, or in this case, the electron, in the hydrogen atom. On the other axis, it's number of electrons. Okay, so there is only one electron in the hydrogen atom. So this peak is pretty small versus helium. Look at helium. There are 2 electrons in the helium atom. So this peak is a little bit higher. Can you kind of tell that that one's a little bit higher? And this is a little bit lower? So the height of the peak represents the number of electrons being removed. And then as I go across, it measures the amount of energy needed to remove those electrons. Now, here's what's kind of interesting. There is only one electron in hydrogen. This is the 1s electron. So the electron configuration like 1s1. In helium, this would be 2s2. The 2 electrons both require the same amount of energy to remove. And now make a couple comparisons here. Removing the electrons in helium requires more energy than hydrogen. And we could explain that again in terms of like electron configurations and atomic structure, that helium and hydrogen are both filling, whoopsie, I wrote a 2. That's a 1. My bad. 1s2. They're both filling the first energy level. But helium has 2 protons and 2 electrons. The 2 protons create a greater attraction, a greater nuclear charge. Oh, well, if there's a greater nuclear charge, there's more attraction within the small helium atom. It's going to take more energy to remove an electron. So they might ask you, like, why is the ionization energy of helium greater than hydrogen? And we would explain that, again, in terms of atomic structure. So the 2 things that we're measuring with this PES data, these PES graphs, the number of electrons in a particular orbital and the amount of energy required to remove one of those electrons. So again, like in helium, there's 2 electrons in that s orbital. If I remove one or the other, they both require the same amount of first ionization energy, which is kind of what they're just explaining here. So I want to look at some more of these graphs. Check out lithium. Here's where it gets kind of fun. How do I know this is lithium? Well, because it says it's lithium, duh. But you could also count the amount of electrons listed. So here's 1 electron. Here's 2 more electrons for a total of 3. This is element number 3, lithium, which is one of the things that they might ask you. They'll give you a graph and say, hey, what element is this? Count the number of electrons. That's on the y-axis, relative number of electrons. Now another thing they might ask you to do is label these electrons. You know, I know the electron configuration of lithium is 1s2, 2s1. Oh, the 1s2 electrons, that must be these. There are 2 electrons in lithium that seem to require about the same amount of ionization energy, 6.26 megajoules per mole. So again, that's kind of giving us some concrete evidence that there are 2 electrons that fit in these s orbitals. There are 2 electrons that seem to carry about the same amount of energy. It takes the same amount of energy to remove either one of them. Then this little guy, he must be the 2s1. Okay, so they might ask me, what element is this? Count the electrons. It's lithium. They might ask me to label the electrons. Okay, well, look at the electron configuration. That usually kind of helps you. Like, okay, there should be 2 electrons that go together. Well, that must be the 2 electrons in the 1s orbital. The single electron is in the 2s orbital. Now, the other thing that I should understand is this trend in ionization energy. Now again, this graph just lists energy. It's ionization energy. We're referring to the amount of energy it would take to remove these electrons. So they might say, why does it take more energy to remove the 2 paired electrons versus the 1 single electron? And we'd say, ooh, I like this. This is the valence electron. These are the core electrons. And we always kind of mention that, we want to lose the valence electron. In order for lithium to become a stable ion, he wants a full outer shell. And in this case, that's only going to be the first energy level. So he'd really like to lose that 1s electron. So the ionization energy of the 1s electron is pretty small, 0.52 probably megajoules per mole. But those 2 paired electrons, now that's the core electrons. They're closer to the nucleus. They're going to experience more attraction to the nucleus. So it's going to take more energy to remove those paired core electrons. Oh, see, PES isn't so bad. It's kind of fun. So let's keep moving. Let's look at boron. All right, here's boron. How do I know it's boron? Because there are 5 electrons listed. There's 1, 2, 3, 4, 5. Now you'll kind of notice that this graph has 2 tiers to it. That's just so that it doesn't go across your paper 5 times. Or it doesn't need like a special insert to show the entire graph. So the lower level just shows from 0 to 10 megajoules per mole. And then proportionally on the top, they would show all the electrons that have ionization energies between 10 and 100 megajoules per mole. And these could have like 3 or 4 tiers to them. It's really just to make it so that these graphs like fit on a standard sheet of paper nicely, rather than like going all the way out to like, thousands of megajoules. Okay, so I know it's boron. There are 5 electrons listed. Boron's electron configuration is 1s2, 2s2, 2p1. So things that they'll ask me, what element is this? They might ask me to label the electrons. Well, I always know that the core electrons are going to take the most energy to remove. So this is my core. These are my valence. So the 2 electrons with the highest ionization energy, those are your 1s2. Those are your core electrons. That's these guys. The peak is a little higher. That shows us that there are 2 electrons that have about the same ionization energy. So we know there are 2 electrons paired in this 1s orbital. We know it's the 1s orbital because these are the electrons that require the most energy to remove. They should be the ones that are closest to the nucleus and have the most attraction to the nucleus. Okay, so now if we look to the second energy level, it should be easiest to remove that p electron. There's only 1 electron in the p orbital. It's a higher energy orbital. And obviously this peak only has a 1 next to it. This is the 2p1. And this is the 2s2. So between the energy level, the electrons in the second energy level, the s and the p electrons, it should be easiest to remove the 1p electron, and then it should be second easiest, I guess, to remove the 2s electrons, the 2s2 electrons. See, this isn't so bad. And again, the more of these graphs that you look at, you get pretty good at analyzing them. They usually ask for really similar pieces of information. So, and again, here's kind of a, more complex graph. It's got 3 tiers. But again, that's just so that it doesn't go across from 0 to 500. And in this case, by kind of breaking it up into these 3 regions, we can fit all the data in a nice little graph. How cute is this? What element is represented by this graph? count the electrons. 2, 8, 10, 10 and 6 is element 19. Element 19 is potassium. Easy, right? And again, we can kind of look at these peaks. It does mark in the number of electrons that have that particular amount of ionization energy. So when the peak is really small, I know that there's probably only one electron in that orbital. Then I had the peak that had a 2, so that probably represents like a full s orbital. There's 2 electrons that have the same amount of ionization energy. Well, they must be paired together in the same orbital, because electrons in an orbital together are obviously equal energy. And then I have this tall peak with the 6 on top. Those must represent p electrons. There are 6 electrons that all seem to carry the same amount of energy. So it takes the same amount of energy to remove them. And then that's just to confirm the fact that 6 electrons fit in these p orbitals, and they're all equal energy electrons. So the electron configuration of potassium, 19 is not too crazy. 1s2, 2s2, 2p6, there's 10. Then I'd have 3s2, 3p6, 4s1. Okay, so here's my electron configuration of potassium as predicted by the periodic table. This PES data just confirms that. You know, I can mark in all these orbitals on the graph. Obviously, the 4s1, that's my valence electron. I want to lose that 4s1. Potassium is normally a +1 ion. So this should be the electron with the lowest ionization energy. That's this guy, 4s1. It's easiest to remove that outermost valence electron. So they might give you a graph and say, like, what is the ionization energy of the valence electron? So I like to think about the electron configuration. And obviously the valence electron should be the one that requires the least amount of energy to remove. Now on the extreme end, the most core electrons are the 1s2. They're the closest to the nucleus, so they'll feel the most attraction. Those should always have the greatest ionization energy. So there are my innermost 1s2 electrons. And everything else kind of fits accordingly. So let's work from the back to the front. These must be the 3p6. Now, if I were to keep removing more electrons, and I only want to remove the 4s electron, that's going to provide me with a stable ion with full orbitals. But if I kept going, obviously the ionization energy gradually increases as I pull electrons that are closer and closer to the nucleus. So next I would remove the 3p6. This would be the 3s2. I keep increasing in ionization energy. Now let's say we go to the second energy level. So these electrons are pretty close to the nucleus. These would be the 2p6. This would be the 2s2. Notice between s and p electrons in the same energy level, it always takes more energy to remove the s electrons than it does the p electrons. Now, s electrons are more stable. They're in a more stable orbitals. So it always requires more energy to remove those stable s electrons. So I like this PES. Not only does it confirm electron configurations, but it also confirms this idea of like orbitals, and that they're filled in a specific order, that they can hold a specific amount of electrons. This is good stuff. And finally, let's check out this guy. Now they tell me it's scandium. Scandium, let's just confirm by counting the electrons. There's, oh boy, 2, 8, 10, 21. Element number 21. Yep, scandium. There they are. And again, let's look at the electron configuration of scandium. 21, I can handle that. That's not too bad. 1s2, 2s2, 2p6, 3s2, 3p6. Ooh, now this is a fun one. 4s2, and then when I hit scandium, it's the 3d1. Oh, good one. I like this. Okay, so now as there gets to be more electrons, I do sometimes like to kind of label them. And so let's go from the core on out this time. The electrons with the greatest ionization energy should be the 1s2. So that's these boogers way on the top. Oh, can I reach it? Yes. 1s2. Those guys require the most ionization energy. The next highest is this 48.5 megajoules per mole. This must be my 2s2. And then these guys are the 2p6. And so again, we said that s orbitals or s electrons are lower energy than p's. So when I compare like the 2s versus the 2p, it always takes more energy to remove the s electrons. They're in a more stable orbital. Next would be the 3s2. So that must be these guys, because they would be more stable than the 3p6. Now watch what happens at the end here. Oh gosh, this is beautiful. Remember how we always said that there's kind of this discrepancy in the filling order of the 4s and the 3d electrons? Oh yeah. The 4s2 electrons, even though they're further from the nucleus, we'd said, you know, like, they should be a little more stable. But now look what happens to the 3d1. So this must be the 3d1. And then this must be the 4s2. Okay, and I can predict that by looking at the number of electrons in the orbitals. Cool. When we form ions, we always remove electrons that are furthest from the nucleus to electrons that are closest to the nucleus. So here's something that kids get wrong a lot. Scandium. Let's say I want to remove 2 electrons. Let's say I want to form a scandium plus 2 ion. Kids will get this wrong all the time. I think we mentioned this with like zinc. That they just want to remove the 2 electrons at the end of the configuration. And so often they'll remove that d electron and then they'll end it 4s1. So they'll end it like 4s1. And then maybe they would have done the shortcut and put like the previous noble gas in front or something like that. And then they get it wrong. Sad face. Now I applaud them on one thing. They knew that scandium plus 2 means lose 2 electrons. That's good. However, we need to remove the 2 electrons that are furthest from the nucleus. We remove the 2 electrons that have the lowest ionization energy, the ones that would be the easiest to remove. Oh, so when you remove electrons from transition metals, be careful. We're going to remove these guys. They're furthest from the nucleus, so this should end 3D1, happy phase. And that's confirmed by looking at this PES data. Look at the ionization energies. The ionization energy of the 4s2 electrons is less than the 3D1. Oh, that's kind of why we show this filling order. Like, we fill them in order of low energy to high energy. And so, yeah, technically, like, this 4s orbital is lower in energy than the Ds. But when it comes to removing electrons, we really have to think about the overall atomic structure. That those 4s electrons are further from the nucleus, so their ionization energy is less. That's kind of what they're getting at in part C down at the bottom. Now, I get it. Usually in the electron configuration, we put the 4s2 in front of the 3d1 to show, like, overall increasing energy of the orbitals. And it also shows the filling order. But when we form ions, we remove the lowest energy, I should say the electrons with the lowest ionization energy, which always means the ones that are furthest from the nucleus. And that's kind of confirmed by this PES graph, that when I start removing electrons, I remove the electrons with the lowest ionization energy. That should be the 4s2. Everything else kind of pans out. Which electrons are represented by this 0.77 megajoule per mole peak? Again, that's kind of why I like to plot it all out. That should be the 3d1. How about the 0.63? That should be the 4s2. Cool. So again, PES data is used to confirm a couple things. It confirms electron configurations. It confirms the number of electrons that can fit in a particular orbital. And it's kind of used to predict, like, how we form ions and how we can plot trends in ionization energy. This is the kind of questions that you would see on an AP type test. If there's anything else that you want to know about PES, let me know. We can have a fabulous lunchtime discussion. Otherwise, I mean, you can definitely Google PES, Photoelectron Spectroscopy. But this is the extent that the AP exam wants you to have an understanding of PES.